Hi, this is lecture 17 of Calculus 2. I am recording this lecture separately from the main class because, well, the lecture in the main class didn't go so well. I kind of got bogged down in some physics details because I'm not a physicist, and I didn't get to as many topics as I wanted to, so I'm redoing the lecture to try to cover all the topics. I'm still not a physicist, so I will do my best to try to explain the physics concepts, but I'm not perfect at explaining them. I'll do my best though. Lecture A is going to be about more on mass, moments and centers of mass, especially trying to explain the center of mass formula is the main goal of lecture A. And then in lecture B, we're going to get into the work done by a force and applying the ideas that we talk about with work to springs, something called Hooke's law, and chain/rope hauling, which is what I didn't quite get to in the regular lecture, but I will attempt to in this lecture. All right, so the goal, again, of lecture A is to try to explain the formula that we've seen already for the center of mass of a thin rod. And to start that explanation, I'm going to consider some simpler cases. Let's imagine we've got two people standing on a teeter-totter. Now, you shouldn't stand on teeter-totters, but I can't really draw stick figures that are sitting down. Let's say one is a child. I'm going to put this child over here, and one is an adult. Standing on a teeter-totter, and let's say the child has mass m and the adult has mass 2m, so the adult is twice the mass of the child. Where should they stand so that the teeter-totter balances, or probably better to phrase it as, where should we put the fulcrum of the teeter-totter so that it balances? I hope it's pretty clear you want the child to be further away from the fulcrum than the adult. And in fact, if the adult is twice the mass, you want the child to be twice as far away. If this distance is L, make a cursive L there, then this distance should be 2L. And this is something that you can verify experimentally. The products of these things have to be equal. 2L times little m has to equal 2m times little l, and in fact they do because of the way that I constructed it. The fact that this person has twice the mass and this distance is twice as far guarantees that the product of the distance and the masses will be the same in both cases. Well, these two things will be the same. All right, I want to think of this a little differently now. The way we're going to think of it is a little strange, but it is a good way to think about it if we want to derive our formula for the center of mass. I'm going to imagine this is on an axis, so I drew over the seesaw there, and I'm going to imagine the fulcrum is at the origin, right there. Okay? And instead of thinking of this law of the lever, so to speak, as an equality here, I'm going to think of it as a sum of two things called the moments of these masses equaling 0 with respect to this coordinate system. In this coordinate system, on this axis, the position of this person would be at L, and the position of this person would be at negative 2L if the origin is right there. The moments of these masses, with respect to the origin 0 are, well, for this mass, it's m times its position, which is negative 2L. That's what it is for the child. And for the adult, it's the mass times its position, 2m times L. And instead of focusing on the fact that these two things are equal, focus on the fact that the sum of these two things is 0. You add these two things, you get 0. The word moments is a little strange. It's not a moment in time. It's just a word somebody made up, I don't know why. That sort of is a measure of each of these masses causing the seesaw to rotate about the fulcrum. Okay? The fact that the moment for the child is negative means that in the absence of the adult, the presence of the child over there is going to mean the seesaw will start to rotate counterclockwise. And the fact that the moment for the adult is positive means that the child was gone. The adult is to the right of the fulcrum, so the adult's presence would cause the seesaw to rotate clockwise. The sum of these two being 0 says the total moment is 0, so there's no tendency to rotate we are at equilibrium, we are balanced. We can apply this idea in another setting. Imagine you've got a number line. Let's mark 0 at a certain spot. It doesn't really matter where you put 0, just pick a spot. And then imagine you've got some point masses on this number line, which you can imagine to be a seesaw if you like. Maybe you've got a point mass right there, another one right here, another one right there, and another one over here. M1, M2, M3, and M4. Now I could calculate the moments of those masses in the same way I did here with respect to the origin. But I want to do something different. I want to pretend, well, I want to calculate the moments of these masses with respect to some other point. I want to pretend like I know where the center of mass is. Let's just say it's right here, just to make something up. That pen doesn't work so well. Pretend this is the center of mass. We've seen in the book that the symbol x bar has been used for the center of mass. In statistics, that symbol is used for the mean of a data set. This is a similar idea, although it's really more of a weighted mean. Let's pretend it's right there. And let's calculate the moments of each of these masses with respect to x bar instead of with respect to 0. The moments with respect to x bar, it's a similar idea. Take the masses and multiply times, well, up here was their coordinates, negative 2L and L. If I'm going to do it with respect to x bar, it's not going to be their coordinates with respect to this axis in this location of the origin, but instead it's going to be the displacement of these masses from x bar. When the mass is to the left of x bar, that displacement will be negative. When the mass is to the right of x bar, the displacement will be positive. The moments are going to be m1 times x minus x bar, x1 minus x bar. That'll be the moment of the first mass with respect to x bar. Notice that since mass 1 is to the left of x bar, its position, x1, is less than x bar, and so this difference is negative. x1, x2, x3, and x4 are the positions of the masses with respect to this number line. The moment for the other masses is very similar. Just change the 1s to 2s, then to 3s, then to 4s. Those are the moments of these masses with respect to x bar. They represent the tendency to cause the seesaw to rotate one way or the other in the absence of the other masses. If M2, M3, and M4 were gone and M1 was the only one there, x1 minus x bar is negative. The moment with respect to x bar is negative for mass 1, and so you get a tendency to rotate in the counterclockwise direction this way. M4, well actually M3 and M4 are the masses where the displacement from x bar is positive, and so they would tend to cause a clockwise rotation. To make it balance, at x bar, which is going to be the center of mass, is going to be the balance point. You want the sum of all of these to be 0. You want that to be 0. The benefit of this is now we can solve it for x bar. We can take this fact that this plus this plus this plus this is 0 and solve for x bar. We can do some algebra. Use the distributive property to write this. And then that has to equal 0. Hope it's okay that I'm doing this as a column. Add m1 x bar, m2 x bar, m3 x bar, and m4 x bar to both sides. Leave these things on the left, say m1 x1 plus m2 x2 plus m3 x3 plus m4 x4. And on the right, where you've got all these terms with positive signs, factor out the x bar. So you have m1 plus m2 plus m3 plus m4 in parentheses and x bar outside of the parentheses Now you can divide both sides of this equation by that sum, the sum of all the masses, to solve for x bar. And in summation notation, your answer would be that x bar is the sum of the moments divided by the sum of the masses. You might say the total moment of the system is the sum of the moments, and the total mass is the sum of the mass, the total mass of the system of 4 points. I'm being a little sloppy here, not putting in I goes from 1 to 4 on the summation, or in general, I goes from 1 to n. This is a point where we won't worry about that. Technically speaking, I should put the index of summation on there. It's understood that this is a finite sum in both cases, I going from 1 to n, where n is the number of particles, point particles. Now, are people point particles? No, of course they're not. But as a simplifying assumption, you could pretend they're point particles as a first approximation, at least, to trying to find the center of mass if you got people on a teeter-totter or seesaw, whichever you want to say. All right, so that's how you find the center of mass for a finite, discrete system like this with finitely many particles. Let's go back to the continuous case of a thin rod. I'm not making my rod thin enough for my taste here. A real thin rod, like a wire, say, a real stiff wire. Let's say of length capital L. We talked about already before the exam how to find the mass of this, integrate the density, and how to find the center of mass. Integrate x times the density and divide by the mass. We already know that. The goal here is to understand that a bit more deeply, and also do something else. I am going to now focus on doing things like the book does and using Riemann sums. And I'll also compare it to the differential approach, differentials being synonymous with infinitesimals, dx, dA, things like that. I'll compare both approaches, and on the homework, I know for this year, and maybe for future years, I'm going to want you to now go back to the Riemann sum approach that the book uses as you do homework problems. Certainly in sections 8.5 and 8.6, I think we're going to have you do that. I can put a number line down here. You can pick the origin to be anywhere you want. Say the left endpoint of the thin rod, and then the right endpoint would be at the location capital L, and say distances in centimeters. Once you've picked a number line like this to measure things with, you would then have your density function, your linear density function, delta of x, linear density function, giving you the density, I should say linear mass density function, in grams per centimeter instead of grams per cubic centimeter. We're effectively treating the rod as a one-dimensional object, effectively as a line, and so we can think of the density as being grams per centimeter instead of grams per cubic centimeter like you usually do with densities. Could have some formula, but let's just think in the abstract here initially. I think for the sake of time, I'm not going to derive the formula for the integral that gives you the mass. I'm going to focus on the moment. Now before we imagine a knife, your hand might be a knife, and you imagine slicing this into a bunch of pieces, infinitely many maybe. In the infinitesimal approaches, those pieces were assumed to have infinitesimally small length. We're going to assume that's not rigorous in the standard real number system. There is no such thing as an infinitesimally small number. Any positive number has a number less than it that's still positive, like divided by 2, for example. We're pretending, though, in that approach that there are infinitesimally small numbers. Now I'm going to do something different. I'm going to pretend that I chop into a finite number of real short pieces that have a certain positive length as an actual positive number like 10 to the negative 3 or something like that. Let's consider an arbitrary chunk that I've cut out. Maybe the left end point of that chunk is at position x. Sometimes the book will call it x sub I. It's going to be a subscript ultimately for a summation. I think I'm going to be even sloppier than the book here. I'm just going to call it x instead of x sub I. We will put it in a summation. You should realize in the summation that there are different x's that we are plugging into the function that we ultimately integrate, or that we, when we are doing the Riemann sums, that we plug into the function in our Riemann sum approximation to the integral. How long is this chunk? Instead of calling it dx, I'm going to call it delta x. So delta x is the width of the chunk. Maybe zoom in on that to make sure you can see that symbol there. So that little curvy brace there, that's supposed to represent the length of the little line segment. It's of length delta x, so I'm pretending delta x is a small positive length, not an infinitesimally small positive length, like I do when I use a dx. What is the moment of the chunk with respect to the origin? Zero. Before I figure that out, I should remark that in this formula for the center of mass for a discrete set of particles, let me re-emphasize one more time, I did say it, that each of the things that you were adding up in the numerator were moments with respect to the origin. These were moments with respect to x bar, but when I derived the formula for x bar, these are now moments with respect to the origin. So I'm going to think about moments of these little chunks with respect to the origin here. Effectively, by cutting the rod up into a bunch of pieces, I've got a bunch of point particles. And the total moment is going to be the sum of those individual moments. Well, let's focus just on the moment of the chunk here initially. I'm using red. I think I want to go back to red. Pretending it's a point particle, it's just the mass times the position. The mass you might call, how about delta m? For the little mass of the little chunk. What's its position? I guess it's x. I'm saying that the x value there along this axis is the position of that little chunk. Of course, the little chunk's got a finite length, so it doesn't really have one position. But if it's real small, x is a good approximation for the position. So maybe I should write an approximately equal to here. To be more clear about that, I'm going to write lots of approximately equal to's today. Well, this begs a question, how do you find the mass of the little chunk? Well, it's related to the density at that point times the length. In fact, delta m is approximately delta of x times delta x. Lots of deltas here. Delta of x times delta x, that is the same as delta m. Right? Because think about it, the units certainly work out. This is in grams per centimeter. This is in centimeters. The whole thing is in grams. It is a mass. If delta x is real small, this product would be a good approximation for the mass of that small chunk. Still multiplying it by x to get the moment of the chunk. What about the total moment now? Which I think I'm going to call capital M. I don't know if that's standard. Sometimes capital M might mean mass. But here today it's going to be moment. And little m is going to stand for mass. With respect to the origin, for the entire thin rod, thinking of it as a bunch of finitely many particles, point particles, just add up the little moments. So now I'm going to say this is approximated, because this is an approximation up here, by the sum of these things. And I think I'm going to rearrange the things in the product to look like this. X times delta of x times delta x. Again, lots of deltas here. Delta of x is your density function. Capital delta x is the length of the little chunk. Technically speaking, the sum I goes from 1 to n, and you should have subscripts x sub I there and x sub I there. Maybe you use a constant delta x. though in the general theory, maybe you allow for even different delta x's. Then you look at this and say, that looks like, kind of reminds me of a Riemann sum. Remember when we did left-hand sums and right-hand sums and midpoint sums? We were taking sums of function values times delta x or times delta t if time was the variable. It's a Riemann sum for the product here. And so in the limit now, as delta x goes to 0, that's the function you integrate. This is not perfectly rigorous either. For one thing, I've got a bunch of approximately equal to things in here, and that's not a precisely defined idea. And you might wonder, does the limit exist? Does it depend on whether you're doing left-hand sums or right-hand sums or midpoint sums? Do you get the same limit no matter what? Turns out you do get the same limit, and it can be proved as long as the function here is nice. One example of a condition that is guaranteed to make the function nice enough is the function is continuous. It actually can have finitely many discontinuities and still be nice enough as well, and even some with infinitely many discontinuities, but we're not going to worry about such cases. We're going to let delta x go to 0 to say that the sum magically morphs into an integral. Is it magic? No. It just feels like magic. Of x times delta of x dx. So I'm integrating the function x times delta of x. As you already know, that'll be the numerator of my formula for x bar in this thin rod case. It's not completely rigorous, and yeah, the summation doesn't morph into an integral. It's not magic. It only seems like magic. It can be rigorously proven based on definitions and theorems that this is what you want to do. So now, therefore, I'll use 3 dots for therefore. The center of mass is what we've seen before. The integral of x times delta of x over the mass integral, which is just an integral of delta of x. I could call this capital M over little m if I let capital M represent the moment with respect to the origin of the thin rod, and little m represents the total mass of the thin rod. That's not standard notation as far as I know. All right. What I'd like to do next is consider a more general kind of example. Not a thin rod, but a thin plate. Let's imagine this plate is a nice object. It has some nice symmetry to it. I'm going to make an isosceles triangle where these two sides are congruent and these two angles are congruent. Let's make the base equal to, say, 10 centimeters, and the height equal to, how about double the base? How about 20 centimeters for the height there? Oops, that's sort of a funny-looking curvy brace. That is supposed to be 20 centimeters. Okay? We're going to ultimately want to find the center of mass of this thin plate. It's a two-dimensional object. The center of mass is going to have 2 coordinates. You might call those coordinates x bar and y bar. I'm going to also assume, for the sake of simplicity, that the mass density is constant, and I'll call that constant delta, lowercase delta. It's not going to be a linear density because this is a two-dimensional object. It's going to be a two-dimensional density, an area density, you might say. It's going to be in grams per square centimeter. Ultimately, I'm going to let it have a specific value so we can do the integral. I'm going to let it equal 5 grams per square centimeter, but I think I'll keep it as a delta for the moment. You could think this is a function of position, but it's a constant function, so you might as well just think of it as an actual constant. Delta. The mass of the thin plate, if the mass density is constant like this, is easily found to be delta times the area of the triangle. 1/2 base times height will give you an area of what? 1/2 times 10 times 20, 100 square centimeters is the area of this triangle. So its mass is going to be 100 times delta. Grams per square centimeter for delta, square centimeters for the 100, giving you 100 delta in grams. This does imply that the mass, little m, is 100 times delta grams. This is a constant here. Just to make things simpler, okay? Because they'll be complicated enough as it is. Well, what about the center of mass? I'm not going to prove this, but I hope it's clear by symmetry, though my picture is not perfect. This triangle is supposed to be symmetric about the altitude here. Same on one side compared to the other. It's a mirror image of itself about that. So by symmetry, the y-coordinate of the center of mass should be on that altitude right there. And in fact, that reminds me, I should put a coordinate system in here, perhaps to make things simpler. Now, I can choose my origin to be anywhere I want. Maybe the apex of the triangle would be a good point to pick, but I'm going to pick the bottom point here on the altitude that's also on the base as my origin. And you might as well pick the x-axis to be parallel to that line and the y-axis to be parallel to the altitude. How can I find, I'm saying x bar should be 0. The x-coordinate, I might have said y-coordinate before. I meant the x-coordinate. The x-coordinate, by the symmetry about the y-axis, the x-coordinate of the center of mass should be 0. It's also based on the fact that the mass density is constant. So there's symmetry. X bar should be 0. I'm not going to prove that, but I hope that's clear. Y bar should be non-zero, though. In this coordinate system, y bar should be positive. And this is 20 up there on the y-axis, and this is 0 down here. Because sort of most of the mass is down low, you should expect y bar to be between 0 and 10, in fact. If you could take this thin plate of metal and balance it on a pin, you'd want to put the pin at the location of the center of mass to make it balance perfectly, which of course is probably impossible to do in real life. Or maybe a machine could get very, very close. But how are we going to find, then, the center of mass in the y direction? It's a similar idea. We want to find the moment in the y direction divided by the total mass. We already know the total mass. What about the moment in the y direction? Instead of just writing down the formula that the book gives you, I want to try to rederive it. And it's really this mode of thinking, deriving these equations, that is the best skill to get out of all this. Okay, we can use the formulas as they're stated for whatever needs we might have, but a skill that's going to benefit you more for the long term is the skill of deriving things. Which reminds me, I did forget to do the infinitesimal approach side by side. Maybe we will want to try to make sure I remember to do the infinitesimal approach here as well. But for the moment, we're doing Riemann sums. You could slice it either way, with slices perpendicular to the x-axis. Although it's probably best, since we are focused on the y-coordinate of the center of mass, to slice it with respect to perpendicular to the y-axis. And in fact, that's better another way. I think the width of those slices is going to be easier to deal with than the height of slices that are perpendicular to the x-axis, because those would have two pieces. But more importantly, we want to slice perpendicular to the y-axis if we want to find the y-coordinate of the center of mass. So these are slices that are not going to be infinitesimally small in height, but have a certain small finite height that I think I'll call delta y. Sometimes the book calls it delta h, h being height. I've already got a y-axis in here, I might as well call it delta y. What's the position of this? Well, why not call it y? Where is y there exactly? You might take it to be the lower value in this small little interval, but you don't have to. You could think of it as any sample point in that small little interval from this point here to this point there. I'll think of it as the lower endpoint there. So we want to find, again, break up the triangle with these horizontal slices effectively into finitely many slices, and find the moments of each of those slices and then add up the moments to get an approximation for the total moment in the y direction. And effectively, we're going to think of these slices as ultimately being point particles, so to speak, along the y-axis, and think of the moments in the same way we did before. Let's see, what should I call some things here? Maybe we should first figure out the mass of this thin slice, delta little m, based on delta y. It's going to be the density times the area, which I might call delta A. Lots of deltas again. Delta, there is the density. This is delta A, which is the area of the thin slice, which will be approximately the width of the thin slice times the height. Now that thin slice is technically not a rectangle, it's technically a trapezoid because of the slanted sides, but if delta y is really small, intuitively, its area is well approximated by the area of a rectangle. So I'm going to pretend it is a rectangle, I'm going to do the width times the height. Ultimately indicating we must be doing an integral with respect to y, so I better figure out how w depends on y. There's two approaches you could take. The book focuses on the similar triangles approach. The big triangle here is similar to this subtriangle. The angles are all congruent. Therefore, by facts about similar triangles, ratios of corresponding sides must be the same. That means, for example, 10 over 20, which of course is 1/2. The ratio of the length of this side, the base, to the altitude there, the height, for the big triangle is the same as w divided by the height of that triangle, which is going to be 20 minus y. Look at the smaller triangle. Its base is w. W is this length here, whereas y is this length there. Its base is w. Its height is this length right there. The big triangle has height 20. Y represents this length right there. Therefore, this length is 20 minus y. You can solve for w. W is 1/2 times 20 minus y, which is 10 minus y over 2. And therefore, I can substitute back up here a 10 minus y over 2 in place of w. The total mass would be approximately the sum of things like this. And integrating this would give you the mass of the thin plate, the thin triangle here. It should give you 100 delta. I think I won't take the time to do that by hand, but maybe we'll have Mathematica do it in a little bit. Instead, let's focus on the moment. Delta capital M of this thin slice, so capital M, it should be its mass, pretending it's a point particle at that point, times the distance to the origin, or to the x-axis, y. It should be approximately y times delta m, delta little m, and that's it. Since delta little m equals this, I can just multiply this by y to get my approximation for the moment of the thin slice. Let me go ahead and put an approximately equal to here as well. I get this. I'll go ahead and multiply this out. 10 delta y minus delta over 2y squared, in parentheses, times capital delta y. The total moment then, in the y direction, for the thin plate of metal, capital M is approximately the sum of these things. stop and say, hey, that looks like a Riemann sum for the integral of this function over the appropriate interval for y in this case. Y goes from 0 up to 20. Let delta y go to 0. The total moment of this triangle with respect to the x-axis, I guess, is perhaps the best way to think of it, is the integral of 10 delta y minus delta over 2y squared dy as y goes from 0 to 20. Then the center of mass in the y direction is going to be that total moment, capital M, divided by the total mass, little one. Let's go ahead and see what Mathematica gives. Initially, we'll keep it in there, the delta in there as just a delta, the little delta. But then we'll also maybe think about what happens when little delta is, say, 5 grams per square centimeter. So that's the integral we want to do there. Of course, it's not too hard to do that one by hand. Treating delta as a constant, integrate that. You get 5 delta y squared there, and you get minus delta over 6y cubed. Going from 0 to 20, you can definitely do it by hand without too much work. But for sake of time, we'll use Mathematica. 0 to 20, 100 delta minus delta over 2 y squared. Oops, forgot my y, didn't I? Y. Integrate with respect to y, that's our moment. And then divide that by the total mass. Percent sign refers to the preceding output. The total mass was 100 times delta. I don't think I need parentheses around the whole thing, but maybe I want parentheses around this part here. 560 over 3 is the y bar, if that's something that can't be right. Oh no, what am I doing wrong here? I'm not sure offhand what I'm doing wrong. Oh, this is supposed to be a 10 instead of 100 there. Thought I found that. That looks better. 20 over 3. 6.6 repeating is y bar, the second coordinate of the center of mass. So 20 there, 10 would be right there. Somewhere right around in there is x bar comma y bar equals 0 23rds center of mass of this thin plate of metal. Okay? It doesn't matter what delta is, actually. I picked delta to be 5 when it lectured for the regular class, but it actually doesn't matter as far as the center of mass goes. Let's end lecture A right there.